If PAEK is a superhero, PAEK is like the true superhero, because not only does it serve these critical applications, but it can actually get there.
There's over 20,000 aircraft today that fly with PAEK components in them. Something like 13 million implants on the medical side that have been implanted that are based on our materials.
We change the crystallization speed. So it crystallizes much more slowly than PAEK. Widen your processing windows.
The geometries can be produced relatively easy with PAEK, LM PAEK, and this is really exciting for us.
Solutionology is about being unyielding with perseverance to get to the solution.
To not give up and to constantly drive for better. So even when we deliver 100%, I want to deliver 110 next time.
And for me, the constraints of that project are the most important, because that's what drives us to a solution. It's all about painting a picture and getting all the details in.
How do we develop a tool that helps share our journey, educate others, and bring more light to the realities of additive manufacturing? The Solutionology Podcast. Welcome to the Solutionology Podcast. And today we've got a couple of really great guests. We're going to be talking about ultra-high performance materials. And it's a topic that is really important to us because so much of our work is centered around solving problems with demanding applications requiring ultra-high performance materials. And it's an area that we spend quite a bit of time, obviously, in fused filament fabrication printing. And so that's what we're going to talk about today. And, this episode is really for a very specific audience. We're going to start talking about PAEK, which is polyether ketone. I always have to remember that. Polyether ether ketone, and it's a material that is printed with FDM, and it enables really high temperature, high performance applications to be successful. And it's a material that's also very difficult to print with. So if you're familiar with the term PAEK, then this conversation is going to resonate with you. And if you're not familiar with it, you might still want to stay tuned in, because it's likely that, especially if you're in an industrial application, there are aspects of your business or applications that could require PAEK, and you just don't know about it. It's not talked about enough because it is so challenging to work with. However, it is used in machining and molding applications heavily in aerospace and healthcare industries. The way that we look at PAEK is it's a superhero. It's able to withstand these high temperatures. It has excellent mechanical properties, and it performs really well in harsh chemical environments. And we're using it in healthcare, aerospace, defense applications, electronics, and heavy industrial. But the challenge for us, and Brian, you can speak to this better than I can, is that it's really tough to process.
PAEK has a very tight window for getting strong parts that don't delaminate, and there's certain geometries that work well with PAEK, but they're very specialized. Setting up a process for PAEK requires a tremendous amount of time to make sure that part is going to come out from a volume standpoint. Each part is going to be the same, and it's very repeatable. So PAEK is really challenging to work with on fused filament side for successful parts.
So most of our PAEK production is truly production, where we're establishing a baseline profile and then producing those same parts time and time again, right?
Yeah, we're not producing prototypes unless there's a very high value prototype that has to be done, because that setup and preparation time on the process controls, it's so unique to each geometry that it's not a plug-and-play solution.
So it's not that it can't be done, it's that the economics oftentimes don't work out for those geometries.
Yeah, the demand for the material properties, it really has to be there to justify PAEK for an application. And in most cases, we can find other materials that solve that problem and meet the requirements. It's just working through that process of education and ensuring that we are hitting the requirements for that project.
I know that every time I'm talking to a client or working on a project and I go and identify an opportunity for PAEK and I get an opportunity to talk to you or talk to the production team, I'm finding faces that are like, in fact, I don't even bring them up anymore because sometimes I'm afraid I'm going to get taken out back and taken to the woodshed. So, but the problem is that those applications still exist, right? And that's why this conversation today is so critical, and why I'm so excited about it, because we're here with Robert McKay and Silvia Berretta, and we're with Victrex, which is a chemical company. And interestingly enough, Victrex invented PAEK back in the 1980s. So there's a lot of history that we've got with Robert and Silvia here today. And taking that one step further, this is where it gets really exciting, is that we're going to be talking about PAEK, which is polyaryl ether ketone. I probably pronounced that wrong, and that's okay. But we're going to be talking about PAEK. And PAEK, if PAEK is a superhero, PAEK is like the true superhero, because not only does it serve these critical applications, but it can actually get there. So Robert McKay is head of new business development and for additive manufacturing, and you've been in this role for over 8 years with Victrex, but you've got a really storied career history in additive manufacturing, and more importantly, ultra high performance polymers. So there's a lot of experience that you've amassed over the years, Robert. We're excited to hear your feedback and perspective. And Silvia, Dr. Silvia Berretta, PhD, you are focused on AM technology strategy, or as your title has it, AM Strategic Technology Manager. And you've been in this role for over 5 years with Victrex, and you also have a very strong background in academic and applied sciences for polymer science and engineering. So this is a pretty special conversation, because we're leveling up the discussion beyond what's the processing window of these polymers and talking about some pretty special things. So thanks so much for joining us, Robert and Silvia. If you wouldn't mind just sharing a little bit about your background in Victrex, that would be really great.
I can go first. So my background is I started as a researcher in laser sintering of PAEK, and then worked with other high temperature polymers. And then when I joined Victrex, I worked with PAEK with the traditional manufacturing processes across a variety of applications, ranging from really consumer goods manufacturing up to implants, medical implants. And then in the last 2 years now, I'm back on focusing on AM in Victrex. Yeah. Rob?
Yeah, and thanks for the introduction, Carl. It's not many times that we get associated with a superhero material and a storied career, so thank you for that introduction.
It's true.
Yeah, so I've been in the industry in high performance polymers and engineering polymers for almost 25 years. I think it feels like now 22, somewhere around there. I'm losing track. I started with Sabic and was in the polyetherimide and their trade name Altem business, so related to the high performance polymers there. And then, as you said, around 8 years at Victrex on additive manufacturing. I'm a bit of a maker myself and love, as we were talking about before we started, the ME background, mechanical engineering background. We love to tinker, and I've got an Ender 3 in the basement, all hacked out, and do a little PLA and ABS printing myself. So it gives a little bit of different color to the job in terms of trying to add it to manufacture with something like PAEK, and having some empathy for what it takes to make it happen, having to play around on my own projects. So that's a little bit about me. If it's all right, Silvia, I'll start with a little background on Victrex to build on what Carl's already mentioned. Yeah, as you mentioned, Carl, 40 years in PAEK. You can blame us for all those faces you get for the fact that the material exists and that it is specified and it works in so many applications. It's the original PAEK. So polyether ether ketone was invented for injection molding. And injection molding is a very fast process. You want to make thousands of parts in cycle times in seconds. It's a very different process than additive manufacturing and printing. So it's not surprising that trying to take PAEK and put it into your machines, that it's really hard to get to work because it wasn't designed to work in an additive manufacturing process. You mentioned some of the industries. I won't go over them again. You hit them all for the most part. That we focus on, just some kind of evidence of PAEK's use in the world. There's over 20,000 aircraft today that fly with PAEK components in them. There's something like 13 million implants on the medical side that have been implanted that are based on our materials. So it's got a long track record and a lot of trust that's built up around it. And that's one of the reasons that when customers come to you and say, I want to add it to manufacture with PAEK, and then you say, well, let's use something else instead, they get a little nervous because they really trust it. And that's the challenge that we have with, how can we make additive manufacturing easier while still giving our mutual customers the products and the performance that they trust. And, I think we'll talk a lot more about that as we go through this discussion. One last thing I'll mention before I turn it back over to Silvia and some of our additive stuff. Little known about Victrex is that we don't just make PAEK polymers. We also use them to make things. So about 3 hours east of you guys in Grantsburg, Wisconsin, we have a gear manufacturing facility where we make high-performance gears. And then in Rhode Island here in the U.S., we have a composites aerospace component manufacturing company where we make aerospace brackets and components with these materials that then fly. And so we manufacture things too, and we want to use additive manufacturing ourselves. So we're kind of on both ends of this supply chain, and we have to live the pain of trying to additive manufacture parts and components with our own materials. And that gives us a little bit more empathy as well into the challenges that you and your customers face.
Yeah, and maybe just to elaborate a bit more how the AM world is in Victrex. So we have what we call an ecosystem. So we have different collaborators, partners we work with. We have a joint additive manufacturing center at the University of Exeter in England, southwest of England. If you know where London is, it's basically 3 hours drive west from London, which for American standards is very, very short drive. Not so much for European standards. And in this center, for example, are located many filament fusion machines for high temperature polymers, laser sintering machines for high temperature polymers. And then we work with other partners and resellers and other research institute to kind of like work on different parts, areas of the AM journey, really, looking at different angles, modeling or post-processing or other specific applications.
Well, it's really interesting to hear that I didn't realize that Victrex has a manufacturing segment of the business, both in the composites and sounds like additive space. That's good to know. Maybe we should form a support group on this whole PAEK topic.
Yeah, I would, not to mislead you, we have traditional manufacturing, and additive is still a journey for us, just as it is with you. So we have some of the same challenges in our own operations of how to make additive manufacturing relevant, how to qualify it, how to make it perform the way it needs to. Everything we're going to talk about today, we have the same challenges and same journey ahead of us.
Well, that's a great transition. I imagine that with that practical manufacturing experience, that had to have been a component that led your efforts to develop PAEK for additive manufacturing, at least in part. Does that sound right? Yeah.
One of the areas that we deal in is, both in aerospace. You hit the two big ones, aerospace and medical, both very interested in additive manufacturing. They have a wide range of parts from those produced in high series parts to those produced in ones and twos. And then the aerospace side, you have the whole maintenance and repair aspect and obsolete tools and these aircraft that have been out there for decades and then having to keep them up. So we definitely had that pull coming in from aerospace, and we also had the customer interest in medical. A lot of the surgeries that we have done are, you get better outcomes if they're customized. We're all individuals and we all have different bodies and different bone structures. And to be able to customize implants for each person is hugely valuable. So we had those kind of trends pulling on us, but yet we saw how hard PAEK is to print and to take advantage of all the advantages of additive manufacturing to try to do those things. And that's what pulled us into this, is to try to make it easier.
Well, we've got a couple unique part geometries on the table here that we'll talk about in a bit. Those were not printed with PAEK, but I won't go any further than that. Could you talk a little bit about the familial relationship between PAEK and PAEK and the polymer and the development, the driving development factors that went into PAEK and the advantages of PAEK materials?
Yeah, so there's a bunch of questions in there, Carl. So maybe I'll start with the background on polyaeroether ketone and PAEK, because there is some misconceptions, and we're guilty of creating some of those misconceptions. So polyaeroether ketone is actually the family name. So PAEK is a polyaeroether ketone, as are there's polyketones out there, there's PEKKs out there. Those of us who dabble in additive manufacturing, high performance polymers, are probably familiar with PEKKs as well. Those are all polyaeroether ketones. So when we started out, and we're going to talk about this this LM PAEK product, that's Victrex AM 200 filament that you've been experimenting with. When we started out with that product, we started in the composite space first, which is also a layer-wise process, has a lot of the same challenges as additive manufacturing. And that's really where we first invented that specific flavor of PAEK. And at the time, we were trying to be smart about differentiation and trying to separate ourselves from the PAEKs that are out in the marketplace. There's lots of different PAEKs out in the marketplace that have been out there for 40 years. And we wanted to make it very apparent that this was something new and exciting and different than what was already in the marketplace. So we messaged it as LM PAEK, and that's the brand. And to some regard, we kind of created a separation between PAEK and LM PAEK that was maybe a little stronger than it had to be. So if you actually look at the chemistry behind LM PAEK, or the AM 200 product that you've been working with, it's really close to PAEK. Essentially has the same exact chemical building blocks. It has them in largely the same ratios. If you look at the polymer backbone, the kind of way these things are all arranged, 80% of it is exactly the same as you would get in a injection molding PAEK. And the only difference is a slight rearrangement, which changes everything when it comes down to manufacturing. So with LM PAEK, you're dealing with something that is extremely close to PAEK that people are used to in injection molding world, and that we've been making for 40 years. And we can get confused by the polyaeroether ketone kind of communication. That's the whole family, is what that is. Sylvia, do you want to just elaborate on some of the, why we did this thing?
Yeah, I think you said this at the beginning as well. So printing with PAEK, it's possible, but it's a challenge, and nearly 100% of the time, it requires an end user that can really trigger the profile settings for a specific geometry. So you have some challenges. It's not plug and play. Well, first you have to have a nozzle and a machine that goes to the right temperature. But it's not a plug and play. So when we looked at LM PAEK, we tried to change a molecular level. We tried to change really some characteristics. So LM PAEK has a 40 degrees lower temperature than PAEK, for example, melting temperature, but has the same glass transition temperature than PAEK. So this means that you can shift a little bit your nozzle temperature, but in terms of performance on the parts, you will have very similar performance of PAEK for the same range of temperatures. This is done not by adding additives, it's done like by designing the polymer structure slightly different. It also, by doing these changes, we changed as well the crystallization speed of the polymer. So in general, just to make everyone aware, polymers can be amorphous or they can be crystalline. Amorphous polymers can be polycarbonate, polyethermide, some amorphous nylon, and then you have crystalline polymers like certain type of nylons and PAEKs. In filament fusion, having amorphous polymer might help. And crystalline polymer might be a little bit difficult. Why? Because when they go, when an amorphous polymer get deposited, it will not crystallize. It will stay there. Instead, with a crystalline polymer, it melts, it cools down when it's deposited above layers, layer upon layer, and then it might move because it starts to arrange itself, crystallize, and maybe warp, or in very extreme case, complete delamination of your part. So with LMPAEK, we change the crystallization speed. So it crystallizes much more slowly than PEEK. So this allows to basically widen your processing windows in filament fusion. So you can, the polymer will not crystallize as fast. It will be able to be deposited a bit easier. The part will not move, will not distort. But also, these characteristics allows it to have a better diffusion of the polymer chains between layers, which ultimately it will impact the interlayer adhesion and ultimately the strength of your parts. LMPAEK has also another characteristic. So I don't know if you have a look at the TDS of PEEK material and you will think, oh, that has a very good viscosity. Problem is that viscosity is measured in a shear range that represents injection molding. So a situation where the polymer really has applied lots of pressure to flow into a mold. That's not the case in filament fusion. The filament goes through a nozzle and then it flows in open air. So there's nearly no force applied. And for viscosity, that matters. So for LMPAEK, with this material, we have a much lower viscosity in a shear range or non-shear range that represent filament fusion, and it's much lower than PEEK. So all these characteristics help to create a polymer that will have better interlayer strength, a wider processing window that can help you also to build maybe bigger parts and on more articulated geometries. And then it's a bit more able to use at the first attempt.
Well, we've certainly experienced that in practice, and it's really helpful to understand the chemistry and the mechanics and the polymer science behind what we get to experience at the printer level. And it has a significant, as you know, it has a significant impact.
Yeah, and also the fact that you can print at lower temperature enables you to use, for example, soluble supports that are available on the market. So again, even more articulated geometries that maybe with PEEK, they could have been very challenging or very expensive because maybe you would have used PEEK as well as a support material, which is costly really. And we also, AM200 can easily be printed amorphous or crystalline. So it could be printed directly crystalline, or it could be printed amorphous and then going through a post-processing annealing process in order to get all the strength and the chemical resistance and the thermostability. We have some feedback that is LMPAEK AM200 is a bit easier to anneal for example, PAEK, because it seems to be in a sort of sweet spot in terms of crystallization speed. So it doesn't deform as much as a PAEK would in a non-restrained air environment annealing process.
Yeah, I think as you were saying earlier, sometimes you can always find workarounds if you have enough time. And, there are slower crystallizing already on the market, slower crystallizing polyaeroether ketones like the amorphous tending PEKKs. And those do print better. I think a lot of you may have even done some of your own work with amorphous PEKKs. The challenge with them is that they, as Silvia was saying, they do have a different crystallization behavior, so it's hard to get them crystalline in their final form. So a lot of times you're stuck with them amorphous, which gives up some of the chemical resistance. The other thing, that they bring is a little bit more uncertainty because they are different. So the E and the Ks mean something in these little acronyms. So they're essentially different chemical structures. There's what's called ether linkages and ketone linkages that build these polyarolether ketones. So PEEK has 2 ethers and 1 ketone. PKK has 2 ketones and 1 ether, which brings some different performance properties. LMPAEK has still 2 ethers and 1 ketone, just like PEEK. So it's much more similar to PEEK chemistry than some of the alternatives. And then you have we see customers try to take polyetherimides, or the SABIC trade name Ultem, and make that work because it is a higher temperature polymer. But that is completely different chemistry with a very different behavior. It does work in some cases, but you have to do all the engineering to prove that it works and be comfortable with that to be able to make that kind of change.
Well, I've got one takeaway. There's a difference between the E's and the K's.
And for us MEs, that's about as far as we're ever going to get in the chemistry, right?
Exactly.
Which is more than maybe some of our audience wants to. But,
well, I just wanted to show my true colors. So Victrex has been developing and supplying a PAEK LMPAEK filament for FDM applications for some time. However, we became connected with Victrex through the Stratasys Open AM and Validated Materials program. Could you talk just a little bit about, that's a new venture for Victrex, that's a new venture for Stratasys. What does that look like, and how do you see that impacting the market?
Well, we're tremendously excited by it because of the kind of acumen of the Stratasys ecosystem and the already existing machine base that's already out there of customers and clients that know how to run those machines and use them for production applications. Up until this time, and it's new, as you said, new for both Stratasys and for Victrex, the Stratasys ecosystem was closed. So they made some and offered some of their own materials, but there was a limited number of them. And we've known for some time that LMPAEK and Victrex AM200, which is the filament version of LMPAEK, would run on Stratasys equipment. But anyone owning a Stratasys Fortis 450 or F900 couldn't access it. So they weren't able to get a spool and throw it on the machine and see how it runs. Mm-hmm. So it's really exciting what Stratasys is doing to bring more materials to their customers and more material innovation. And we feel very privileged to be in the first wave of that activity. There's lots of challenges to that. Stratasys has, you've got very specific specifications to be able to run well on their machines that we have to be able to meet. And that's work we've been working together on over the last, it's been over a couple of years now. I think we've been working together. But we're really excited to be at the other end of that pipe. And I think you were one of the first beta customers to get a hold of some AM200 spools. And it's so exciting when that happens. I think we all kind of secretly emailed around, DI Lab just got some spools. It's a moment. It's a really nice moment to see how things work when they get in a real user's hands who's going to put them on a machine and try to make things. So really happy that that's happened and happy to continue to work together with you and Stratasys and your customers even as this continues.
Well, we are too, and that when we heard, so at that time we didn't have a 450. This was a couple of years ago now, and we were talking to Stratasys, and we were exploring expansion of our high performance polymer extrusion side of the business. And we've always been intrigued by their Stratasys machines, but we've always run open source because that's what we have to do for these, obviously for these other materials. And they shared with us that they were going down this path and that they were open to having us be the first beta. And PEEK was, in this case it was PAEK, but we didn't know it at the time, was the driver behind that. So we've been really looking forward to getting to this stage. For us, and talking to Stratasys, it's been a couple years in the making. And so when those boxes arrived of the filament, arrived in our office, we were also very excited. I think it was physical interaction rather than, going and talking to each other rather than email, but we're in a smaller business. But, right away we got to work with the PAEK, the LM PAEK, and running it on our machine and produced, this might be the first part that we produced. So this really unique organic shaped geometry was the first part that we produced, and it was really a test. We loaded the LM200 along with the soluble support material into the machine. We set the profile, just the base profile, and went to town. And this part came out the very first time we ran it, and we were all blown away. In fact, we went into that thinking that we're going to have to do a lot of work in order to get this part to produce because of the geometry and wall thicknesses. So you went with us. You went from us being extraordinarily excited to see the boxes on the shipping and receiving area to now we're your biggest fans, because the amount of time that it would have taken us to even approach a geometry like this with an alternative material would have been hundreds of hours. So this is we see this as a transformational material that's going to enable applications that simply weren't possible before, not because they couldn't be printed necessarily, but because the economics and the time investment just wasn't possible. So we're really excited about the application opportunities with LM PAEK. See it as simply transformational.
Yeah, we were excited to get those boxes in, but I think there was also a hint of stress and anxiety, not knowing what the outcome would be. And from our past experience, as Carl shared, it's these high-performance materials are never operate right out of the box. It requires a ton of learning and process development so that we can apply that to geometries. And for us with LM PAEK, it's been a reverse. It's been mind-blowing for us to plug in really organic geometries and have those produced. We're fine-tuning some of the parameters, but we're not starting from scratch. It's like we're making minor tweaks to it that have a pretty big outcome, but the geometries can be produced relatively easy with PAEK, LM PAEK, and this is really exciting for us.
Yeah, we know it's not. I mean, it's really wonderful to hear that kind of feedback, because that was the goal with the material. But we also know there's still a lot of work ahead. And you mentioned some of those minor tweaks you have to make, to be able to tune it. It was really nice to be able to see someone who knew how to tackle that in DI Labs. I know you had run some PEEK before and had already gotten a feel for what knobs to turn to try to optimize it, and how quickly you made some tweaks and got even better performance out than you got right out of the gate. So there's still learning ahead of us. It's certainly, maybe compared to PEEK, and it's kind of an old traditional injection molding form, it's almost plug and play. It's certainly not plug and play all the way. Though I'm hopeful as more of us get to work with it and do some more optimization, and Stratasys continues their work on it on their machines. And we learn more about how to advise customers to set profiles, that'll get even easier.
Yeah, we're probably in a unique position with our experience with PAEK and PES and the other Ps out there that we've had to produce parts out of. We've really skinned our knees and built a great knowledge base so that we can operate within some of these areas and be really effective at iterating process and coming out with an effective printed part. So we say it was easy, but it may not be. Yeah, you're right. It may not be the same case for everyone.
Certainly easier than PEEK.
Yeah, that's for sure.
So you were talking, it was really interesting to hear your story about the introduction of LM PAEK, Robert, and the desire to create differentiation between PAEK and PEEK, and maybe even to the extent that there was too much differentiation created, because now we're in a place where we want them to be similar because we want PAEK to be swapped out for PEEK, or vice versa. Can you talk to us a little bit about what you're seeing in terms of acceptance of PAEK and traditional PEEK applications? What are the successes of adopting PAEK in place of PEEK?
So I'll start, and then Silvia will also share some of the recent work we've been doing. So first, just to recognize that we, as you mentioned earlier, there's two flagship markets of greatest interest, aerospace and medical, are also tend to be some of the more regulated and more conservative industries. So there are certainly going to be early adopters, and there are also others that are going to take more time to feel fully comfortable with whether or not, it's very similar or not, it still performs different. And in the end, for qualifications in aerospace and medical, it's not the material alone, it's the manufacturing process plus the material that has to qualify. So even if you had PEEK, you'd still have to qualify and add it to manufactured PEEK in aerospace and medical, and that will take you just as much work and actually be harder because it doesn't print as easily. But you still have to do that work. So I don't want to mislead us and think, oh, it's just plug and play, drop it in, and it's airspace qualified today, we can start making flight components. That's not the case. We have a long journey ahead of us. But we are pretty comfortable that this material is going to, as we go through that journey together, with a machine material pairing like the Stratasys combination with Victrex AM 200 filament, that we will successfully get to that end goal. And one example in composites, we mentioned composites is the first adopter of this LM-PAEK material. It's already being qualified in composite form for flight uses. So I think it's Wichita State University, their NIAR center, who does some of the aerospace qualifications, has already qualified some LM-PAEK thermoplastic composite materials that include this polymer, exact same polymer, that have qualified for flight uses. Those of us, your customers who are in the aerospace world and who may have dabbled in composites, we call that Victrex AE 250 composites is the kind of trade name in the composites world. This polymer that you're printing with is the same one that's in Victrex AE 250. Viscosity is tuned for the additive process, but the polymer chemistry is the same. So it's already being qualified in aerospace. I think some of the lower or the quick adopters are the places where you need this performance. You need some of those parts you showed there where you have like a complex manifold or fluid engineering, kind of the industrial, you're trying to solve a machine problem in a manufacturing environment where you don't have to qualify for flight or medical implant. Their adoption can happen quickly. But we will have to go through a journey on aerospace, commercial flight especially. You'll see maybe early adoption in some space satellite defense applications, perhaps, some low sensitivity applications, interiors perhaps. But the further you get into higher performance flight components and the further closer you get to medical implants, it's going to be a lot longer journey. Silvia's been doing some work to help us close some of that gap. Maybe you could share some of that, Silvia.
Yeah. So one of the I think one of the main things we need to tackle with LM-PAEK is that PEEK has been around for 40 years, so it's been used for 40 years, and we had nearly 40 years to go after various certifications and qualifications. So one of the first things that I'm looking at as part of my role is to identify what certification we need to go for first and what are the most important for our customers. So we already done some of them. So we and the results are very good, are very positive because they're very similar to PEEK. I'm talking about like UL flammability or outgas, initial cytotoxicity, for example. And the results are very positive, very similar to PEEK, exactly passed in the same range. We also know that one of the applications where PEEK is used is for in a corrosive environment. So we're looking at the chemical resistance of LM-PAEK. And we're doing this in a deeper level. So we are like looking, okay, what if it's molded? What if it is left as printed but left amorphous? And what if instead is printed and crystalline? So And then we could see that, of course, as expected, we could see that amorphous are much less resistant to chemicals than crystalline forms.
Yeah, you can choose to leave it amorphous, like this, or you could crystallize it like that. And if you crystallize it, you're certainly going to get higher chemical resistance. If you leave it amorphous, we certainly see that the chemical resistance printed and even molded amorphous is lower than you would have with crystalline PEEK with an amorphous LMPAEK. But when you crystallize it all the way, which you can do with LMPAEK, then your chemical resistance is really right in the same range as PEEK. Everything that Silvia's tested so far has pretty much come up identical as PEEK. Now, certainly there's a huge world out there of corrosive chemicals that we haven't tested them all, that we still have a journey to go on there, but any kind of the early work we've done is showing a pretty good performance in chemical resistance and corrosion resistance of this LMPAEK versus your traditional injection molding PEEK, as long as you crystallize it. Now, not every application needs to be crystallized. You still get pretty good chemical resistance, even amorphous, and that's one of the pretty cool things with additive is you can choose. Do I leave it amorphous or do I crystallize it? Do I do my prototyping amorphous and then do the annealing afterwards once I'm comfortable with the shape and the function of the part? You have that choice. In molding, you don't get that choice. It comes out crystalline.
It's really powerful to see the color difference in the two parts that you have there, the one that's amorphous and the one that's crystalline. I don't think we've seen that drastic of a color difference in any of the documentation that I've gone through.
No, I'd say most of the parts that we're producing are semi-crystalline, so they're between fully amorphous and fully crystalline.
Yeah, you're on the Stratasys equipment, and your chamber temperatures are probably up there. I don't know what your settings are, like 130, 140, something in that range. You can really quench it harder. So if you wanted to make it more amorphous, you could. I wouldn't, but you could if you wanted to.
So what temperatures, do you know off the top of your head, Robert, what temperatures we'd want to anneal these at, or temperatures or times for to get to a fully crystalline state? I'm sure it's dependent on the thickness and everything.
Yeah, I'm going to leave that for Silvia. She's been doing a lot of work in that area. Usually it's in the 160 to 180 range for some hours.
Okay.
But depending on, if you're already starting with some crystallinity, it can be faster. And you can always ramp faster or ramp slower depending on the situation. But the one thing we do see, and maybe you're doing this in your work, some geometries are less stiff or resistant to deformation than others. And so certainly you can open air anneal this more than you could some alternatives, but in some sensitive geometries, anything really with very low geometric stiffness, you will see it kind of collapse on itself or deform as you try to anneal it. And so annealing in sand or other kind of inert media like that can solve that problem and eliminate it for large part.
We would recommend it to stay away from. So in order to anneal, you need to be above the glass transition temperature of the polymer, which is 150 degrees Celsius. So we say at least 10 degrees, so 160s or above. And of course, it will need to be maybe. We will never recommend it to put your oven or furnace at temperature and then throw your parts. That will be it will give the part a bit of a thermal shock. We will recommend it to slowly heat the part up to temperature within the oven and leave it your annealing temperature of choice, the one that you optimize for a particular geometry, for a couple of hours at least, and then it might need some tweaking, and then slowly cool down as well. We know that it's possible, and it helps to maintain geometry to anneal in different medias. So like sand or gypsum, it could vary a bit on your part. We also know there's a rule of thumb in general with the PAEK materials is that if you know that your part will be used at a certain temperature, so let's call it your application or service temperature, then anneal 20 degrees higher than that, because that will ensure that when the part is in place in the application, it will not change. It will not go into any relaxation.
That's really helpful. We were talking about the fact that as we're producing these parts, we're probably producing them in a semi-crystalline state, so not fully amorphous and also not fully crystalline. And it was really helpful to see Robert shared a couple of parts on the screen. It was really helpful to see the stark contrast in color of those two parts that allows us to push the boundaries a little bit more on fully crystalline, getting the parts fully crystalline through the post-processing.
Yeah, and it's good when you see only one color on the part. It becomes a problem when you see both, and it was not desired. Yeah.
Do you foresee any time where Victrex might start to introduce reinforcement additives into the filament, like carbon fiber or fiberglass?
Definitely, yes. Yeah, it's something we're already working on in the background. So yes.
Well, that's something
Definitely.
that we'll be mighty excited to. We're awaiting that now as we speak, and we'll be excited for that launch. In fact, if you're looking for any beta users of that, we'd be happy to do that. There's a lot of applications that we venture into that require that level of stiffness or reinforcement. And from our experiences so far, being able to work with PAEK as a base material would be as transformational as what we've already experienced. There's no doubt about it. Yeah,
and just be mindful that according to the fillers, you might need to have some additional checks. So just to be on the advocate level here, like if for carbon fiber parts, for example, they will be black, so you will not be able to see if your print is stable. Your printing process is fully stabilized, because you will not see what is amorphous and what's crystalline. Okay, it's all black. So then when a filament like this is in your process, you need to make sure as well to check really the crystallinity content in your parts, and to be methodical and how it will be. And that will be, it's part of the journey with fillers, really, especially with black fillers. Yes.
Yeah. We've had a lot of requests for black filament because it hides the crystallinity, but there's a double-edged sword to that. If you hide the crystallinity, you can't see how in control your process is. And you want to be able to see it if you can. Now, black carbon filled, you won't be able to. So as Silvia said, you'll have to overcome that different ways. Yeah, it's something to talk about. So we have a prototype, and we talked about this last year at CAMX, at the CAMX conference. Silvia presented there. If you were part of the proceedings, you can go look that presentation up. We can send you the content from that as well. We are doing a carbon filled short carbon filled fiber version of AM200 filament. That's in the plan, and there's already prototypes available. So with your kind of full open material license that you have access to, we may even be able to get material to you now if we talk that through with Stratasys, rather than wait for Stratasys to kind of evaluate it and qualify it. We can start that now.
Do you see any particular request for some type of fillers?
I'd say the fiber filled is probably the most prevalent, whether it's carbon or glass fiber.
We prefer, if we can run glass fiber over carbon fiber, that would be our preference, just because of the reduction in abrasion that we see on the equipment. We lose some stiffness there through that glass fiber reinforced rather than carbon fiber, but if the demand isn't there on the application, then I think there's an advantage on the processing side.
Yeah, we just ran some glass fiber prototypes a couple weeks ago, so the work's being done. I think, and that is a great question Sylvia asked, because we get the maybe misleading impression that carbon fiber is the more in demand. So we're kind of starting with carbon fiber, but if it's the other way around, we can always change the schedule.
It'd be interesting to review some of our recent projects where we've had specific stiffness requirements for geometries we've produced. And then if you've got material properties off of your finished carbon fiber versus glass fiber, then we can compare those and see where that would end up.
In the AM industry, it's still quite young, right? So we're and oftentimes we're approaching projects, or we find that projects are approached in a little bit cavalierly, and not necessarily in a negative way, but we don't have the legacy of injection molded materials with injection molded material testing to really understand what provides us with the greatest strength or suitable characteristics for our applications. So there's a lot of cases where we'll find that parts may be overspecified based off of intuitive or just practical knowledge rather than truly understanding the needs. And that's not a bad thing because, in some cases it's okay, in other cases it's just overkill. And there's this other component that, the whole conversation of crystallinity versus amorphous, those aspects of the conversations usually don't take form in specification. And so there's this side of additive that needs to mature yet so that we really understand what we're specifying to make sure that it fulfills the application. And in the case of carbon fiber requests, I'd guess that there's a lot of carbon fiber requests because there's some conservatism in that over fiberglass. And obviously that's not talking to all applications, it's just an anecdotal perspective, but we see that quite often in our scenario.
Something we've seen is kind of the reverse, where it's the print bureaus themselves that are driving carbon fiber, because they get a customer coming in and says, I want PAEK. And then they try to run PAEK like you described, and they have a miserable time of it. And then, if I put a little filler in there, it starts to counteract some of the shrink and warp and makes it a little easier to work with. So I can go back to these customers and say, well, use this carbon fiber PAEK because I can actually print it when I couldn't print unfilled PAEK. So we feel like some of that will go away with LM-PAEK and Victrex AM 200 filament, where you can use the unfilled PAEK and get it to print well enough and not have to throw the fillers in there to solve the problem. Yet there are still, so that's a piece, there are still applications out there that want filler for good reasons. Temperature resistance, so these polymers soften as they get past their softening temperature, their TG. And if you have fillers in there, you can boost that 10, 20, your use temperature 10, 20, 30 degrees, depending on the situation. So that's a real case for having, filled filaments. And so we know we're going to need filled filaments. But in the cases where you can get AM200 to do what you need it to do, you don't have to throw the filler in there just to fix the problem.
Agreed. Well, this has been a really enlightening discussion. Outstanding to hear the history of PAEK and PAEK and the adoption and testing that's being done on PAEK to drive greater adoption. If you were to give advice to an organization that has traditionally used PAEK and could explore PAEK, what advice would you give them?
Maybe from my side, I would say, if you can pick up all the failures that you had with PAEK, have a go with LM-PAEK, and then and see what happens. And what we'd expect is similar to what you said, really, that geometries that you would not think, they will be printable with PAEK, but after how much time, you will see them printed out the first time, right? So I think that it would be, it's such such a significant difference. That would be my advice. Pick up all the failures and try them with LM-PAEK.
And mine's similar. It's you're gonna have to go through a journey. You can't, even if you had PAEK, you still have to qualify on the machine and the printed part. And you've shared some of the challenges that most of our customers actually ignore that. They give us PAEK, we tell them you're going to have a hard time of it, and they insist on having it anyways, and they go and try to print it, and then come back and say it didn't work very well. So my advice would be, understand you have a new process here. You're going to have to go through a qualification process. Why not go through a qualification process you have a chance of succeeding in? And the closest material that actually works really well is LM-PAEK. And so choose that to go through that journey rather than trying to force fit other things that are maybe a lot different than PAEK and trying to do it that way, or trying to force PAEK to work when it really doesn't work very well. And maybe that's a bit of an overconfident statement in terms of, choose LM PAEK as your candidate to go through the process with, but that's how it feels for us right now.
Well, it's well-founded from my perspective with the history that you both have and the history that Victrex has in polymer development in both PAEK and PAEK, and the manufacturing operations that you have. To me, that resonates very clearly that there's a strong foundation that's driving that feedback and advice. So thank you both for that.
Thank you
for
inviting
us. Yeah.
My takeaway is that, as we first heard about LM PAEK and, not digging into the details, our sights were on PAEK, and we had to have PAEK because that's what was demanded. And when we first heard about LM PAEK, we were like, well, this isn't what we need. We need PAEK. We need to be able to specify this to clients. But after this discussion, I think that we've got some confidence and foundation built that we can better align LM PAEK with PAEK applications because the differences are small, and we'll work on communicating that through rigid data that we can provide. But we're not as far off as what we expected we would be from PAEK to LM PAEK. So I think our objective coming out of this is working on our communication and terminology so that we can tie those together as we're working on applications.
Yeah, and I hope you bring those parts next week to Rapid. I can't see them up and close, but from this distance, you should be proud of those. Those are really good-looking parts from really complex parts, and to get them out of your machine with only, obviously you had your expertise and doing some of the tweaks you did, but you should be proud of that output. I can't wait to see them up close.
Well, now we have to bring them, Robert.
Yeah, you do. Another suitcase.
Thanks so much, Robert. This has been a lot of fun, very informative, and absolutely one of the most enjoyable topics that we've got. And we're looking forward to helping expand the adoption in the market for LM PAEK because we see that this really starts to open the doors to applications that otherwise wouldn't be easily solved.
Thanks, Carl.
Thank you both.
Thank you.
That's fine.
Thank you.